Alright, ladies and gentlemen, today we're going to be wrapping up some stuff with momentum rotation, and we're going to be just doing a real quick unit. I wouldn't even necessarily call it a unit. It'll just last this week, and you'll have a quiz coming up this, just within a few days. See the Canvas sheet for more details. But so what I wanted to do is kind of continue to draw some analogies between the linear situation that we looked at here, P equals mv, and the rotational situation here. So P, of course, means what? I think you all hopefully told me that means momentum, M for mass, and V for velocity. In rotational momentum, there's a rotational momentum. When something is spinning, it's going to tend to continue to spin. And the symbol for rotational momentum is a capital L. Why they chose L, I'm not really sure, but that is what is used. What should we use for the M? Instead of M for mass, we want to talk about rotational inertia, and the symbol for rotational inertia is an I. Okay. And instead of linear velocity, we want to talk about rotational velocity. And the symbol for rotational velocity is, hopefully you remember, the squiggly W, also known as a lowercase omega. So L equals I omega. And this will be on your equation sheet as well, your AP equation sheet. So that's the equation that we're going to start with. Angular momentum or rotational momentum used interchangeably equals I, your rotational inertia, times omega, your rotational velocity or your angular velocity, whatever it's called. Sometimes this might be called your moment of inertia too, instead of rotational inertia. It all means the same thing. Those were some things that were kind of confusing me when I saw them after later on. What's the difference between rotational inertia and moment of inertia and moment arm and lever arm? And it's really just the same thing. So the units on angular momentum or rotational momentum is kilogram meters squared per second. Not that that's the most important thing in the world. Notice that they leave radians out, which technically would be in it if we were to multiply these two together, but it's just for a matter of convention. Radians is left out. So now, when we looked at momentum, remember that change in momentum was equal to force times time, where that's known as the impulse. So change in momentum equals impulse. And there is an analogy for rotational momentum as well. When we talk about, instead of linear momentum, what do we just say the symbol for rotational momentum was? The L, so delta L. And instead of talking about forces, when we talk about rotation, what's a force in rotation? Or what force causes rotation? That is torque. Okay, and then delta T. So just the analogous, change in momentum equals force times time. Change in rotational momentum equals torque times time. Okay, so here we've got a pulley with a radius of 30 centimeters. It's spinning with a rotational momentum of 2 kilogram meters squared per second. A string along its edge pulls with a force of 5 newtons for 6 seconds. What's its final rotational momentum? Okay, so we're looking for its final rotational momentum, which means we want to know the initial momentum and the change in momentum. So it tells us the initial momentum is 2 kilogram meters squared per second. So that means we need to find the change in momentum, which is torque times time equals delta L. Okay, so in order to know that, we got to know the torque. Now it tells us that the string pulls along its edge with a force of 5 newtons, and that has a radius of 30 centimeters, which means it's pulling 0.3 meters away from the center of the pulley. So the lever arm is 0.3. So our torque is 5 times 0.3, which is 1.5. Okay, plugging that into our delta L equals torque times time. Okay, we just found torque, which is 1.5 times our time of 6 seconds, gives us 9. So we know we started off with an initial rotational momentum of 2 our momentum is going to change by 9, so our final momentum is 11. Okay, so just kind of a basic problem. I try to cut out most of the finer details and just cut to the root of the problem there. So linear momentum we looked at was conserved because of Newton's third law. Okay, whenever two objects, whenever a cannon fires a ball, the ball fires the cannon. So if we start with an initial momentum of 0, as long as there's no outside forces, after firing we should still have our sum of initial final momentum of 0. So in this case, -5 plus 5. We've got a leftward moving cannon and a rightward moving cannonball. Our sum would equal 0. Rotation works the same way. Okay, in linear momentum, if we have a collision, okay, if we have a 1 kilogram car moving at 6 meters per second, crashes into a stationary car. Afterwards, we've got a 3 kilogram car system moving at 2. So we've got 1 times 6 gives us 6 kilogram meters per second. After our collision, we've got 6 kilogram meters per second. So the momentum is just distributed among a larger mass. Okay. So rotational momentum is also conserved as long as there's no outside. Now instead of forces, when we're talking about rotation, we're concerned with torques. Okay. And we can abbreviate that by saying L1 equals L2. My initial rotational momentum equals my final rotational momentum in a rotational collision, or explosion, or something along those lines. And we can expand that by saying I1 omega 1, so my initial rotational inertia times my initial rotational speed equals my final rotational inertia times my final rotational speed. So this is also has to do with Newton's third law. Makes this a definite situation that is true. So here is an example of a rotational collision. And again, I've tried to make this a fairly basic one. I didn't have you calculate the rotational inertia of anything, whereas you probably do that on problems that you were doing. So here we've got a disk which has a rotational inertia of 1.5 kilogram meters squared, kilogram meters squared per second, rotating at, that shouldn't be per second, that should just be kilogram meters squared. Rotates at 3 radians per second. A bar with the rotational inertia at 0.5 is dropped on it. What's the new rotational speed? So we're starting with initials of inertia of 1.5 and an initial speed of 3. Okay, so my initial rotational inertia is 1.5. My initial rotational speed is 3. So that's my I1 omega 1. Okay, when I drop the bar onto it, so my I2 is equal to the 1.5 plus the 0.5, which is the bar that I add onto it. So equals 2, and then that's going to equal that times my final rotational speed. So dividing, we get 2.25 radians per second. So I1 omega 1 equals I2 omega 2. Now, what's kind of cool about rotational momentum is that you can change the rotational inertia without actually changing the mass of the object. All you have to do is move the mass around a bit. So here we've got a person with their arms with some dumbbells out, and then here they bring them in. Okay, so here they're having a large rotational inertia with their arms out. Okay, because when you bring mass away from the axis of rotation, you have a large rotational inertia. As you bring the mass towards the rotational axis, you decrease the rotational inertia. So with large inertia, small inertia. Now in order for momentum to be conserved, okay, when my rotational inertia goes down, my rotational velocity must go up. So their radians per second increases when they bring their arms in. This is similar to a figure skater when they bring their arms in or out. Okay? When they start with their arms out and then they bring their arms in, their rate of rotation increases. This is just rotational conservation of rotational momentum. Okay? When their arms are out, they have a higher inertia, and and a small velocity. Okay, and when they bring their arms in, they have a small inertia and a larger velocity. Okay, this is how divers control their angle of entry into the water. They can enter into a tucked or an extended pike position, and when they're getting close to the angle of entry that they want to extend into an extended position to slow their rotational rate so that they enter the water at the right angle. We can think of a planet going around a sun as another example of conservation of momentum. If we think of the rotational inertia of a planet equal to mr squared, which is one of the equations that I gave you from last unit. So when they're close to the planet, they have a small radius and therefore a small rotational inertia, and they have the greatest speed. And then as they travel outward, they've got the planet has a larger inertia, a larger radius, mr squared, a larger inertia, okay, and a smaller rotational rate. The velocity goes down. Okay, so angular momentum obeys the right-hand rule just like all the other ones. Here they've got a picture of the person. They're showing the direction of the angular momentum. Notice the fingers are curled in the direction of the rotational rate, the rotational direction, and the thumb points in the direction of the momentum vector. Okay, so objects that have momentum resist changing what they're doing. A speeding train has a lot of momentum. It's very hard to get to go back the other way. In the same sense, objects that have a lot of rotational momentum will also will resist changing the way that they're pointed. Just like the train doesn't want to go a different direction, this gyroscope doesn't want to go a different direction because of its rotational momentum. This is normally where I would start showing you some things in class. So if you're in class, you'll get to see some things, some demonstrations. If you're not, there's nothing I can do. Sorry. But you can take your bike and you can go for a bike ride and experience gyroscopic stability. Once you're moving, the wheels act as gyroscopes, and they resist changing the direction that they're pointed, and you stay tilted the right way. Okay. And lastly, the last topic that I want to cover with rotation is rotational kinetic energy. Okay, so when you throw a sleeper, you throw the yo-yo down, and it's spinning at the bottom of the string, and it's just sitting there at the bottom of the string spinning, and then when you give it your hand a little twitch, it climbs back up. Okay, how does it have the energy to climb back up? It looks like it's not moving. Well, of course it is moving, and in order to climb up and increase its gravitational potential energy, it must have some other energy that it can convert, and that is rotational kinetic energy. So let's figure out what the equation for rotational kinetic energy would be. So normal linear kinetic energy is mv squared over 2. Okay, so for rotational kinetic energy, instead of m, we're going to use what? We're going to use I. Okay, and instead of v, we're going to use what? We're going to use omega. Okay, so the symbol of the equation for kinetic energy equals I omega squared over 2. Okay, so a wheel that's rolling down a hill has got both types of kinetic energy. It has both linear kinetic energy as well as rotational kinetic energy. We have to take both of those into account if we're doing a decent analysis of a rolling object. So let's say we've got a 3 kilogram hollow wheel with a diameter of, or a hoop, with a diameter of 1 meter, rolling along at 4 RPMs. What is its linear and rotational kinetic energy? Okay, so the first thing I choose to do is put everything in the correct units here. For its omega, we're going to convert 4 RPMs. We're going to convert that into 0.419 radians per second. So 1 rotation equals 2 pi radians, okay, and 1 minute equals 60 seconds. So minutes cancel out, rotations cancel out, we're in radians per second. We want to get that diameter in terms of the radius. It's going to have a radius of 0.5 meter. Since it's a hoop, the rotational inertia is going to equal mr squared. So that is 3 times 0.5 squared, so 0.75. And first off, we'll calculate its rotational kinetic energy. That's I omega squared over 2. So we just calculated I, we just calculated omega. Okay, so 0.0658. The next thing we want to do is figure out its linear kinetic energy. And the first thing we want to do is figure out what's the actual velocity of the wheel rolling along. Okay, well, V equals R omega. Right, that whenever to get to the linear, we multiply the rotational times the radius. That's kind of the rule of thumb that I wanted you to get in your noggins. So 0.5 times 0.419 radius times the rotational speed gives us a linear speed of 0.21. Okay, and then kinetic energy equals 1/2 m, which was just 3, okay, times the linear speed 0.21 squared, and we get 0.0658. So these are identical in this case. Had the wheel been a different shape, then these would not have been the same. But based on this shape, they are the same. And that is it for rotation for this for AP Physics 1, and we're moving on to other stuff. So let me know if you have any questions. Come to my virtual class period / office hours.